Hello, have you ever tried to tell someone why 100% availability is not a thing? My name is Igor, and today we're going to talk about this. So what we're trying to do is to explain this in a very simple and basically simple way to stakeholders that this is actually not a thing. To do this, I'm going to introduce you to a new kind of service. It's still kind of under NDA, but it's just amazing. So, are you thirsty? Because now I want to introduce you to my new Lemonade as a Service thing. So, this is a new thing where all SREs, we know how to make services, so let's go to it. First of all, we need some market analysis, of course, kind of this boring stuff. So I'm going to find out that the Lemonade has to cost $250. We have a 24/7 service and a bunch of other things as well. So, next thing that we need is just a recipe. We need to create some lemonade, right? So I'm going to use my old family recipe using some organic lemons, cane sugar, water and ice cubes. And our lemonade price is now at 79 cents. So it's a good price, but it's not all the costs that we have. We also have a couple of fixed costs. For example, we have electricity, we have permits, and we also have capture expenditures for all the equipment that we need. So with all this, if we take all together, we come to a new price of the lemonade that I call the break-even point. Our break-even point, I'll keep this on the up right side of this calculation. So this is actually not the whole truth because I actually need people to sell my lemonade. So first of all, we are hiring 10 euros per hour. It's going to make my price quite high, but we have this very wealthy angel who is financing this thing. So we go live with this. And it's actually a huge success. People forming lines to get a lemonade are still making a lot of losses, but that's actually okay. In fact, it's going so well that we're hitting our first problem here. It's actually going too well. We're running out of capacity, and we're not hitting our time to lemonade SLA. So what can we do? There are a few things that we can do. First of all, we can try to scale this thing a little bit elastically and create more lemonade stands, right? And we can do this smarter. So in this case, we just hire people for the peak times. So basically, during the night, nobody buys lemonade. We have just one person sitting there for the 24/7 requirement. We can also actually do this with machines. Sorry, we're no longer hiring because this is actually cheaper. Now, this is my new automated lemonade stand robot that's selling lemonades for us. My price went now to $112. However, machines break. So we need maintenance contracts, and we know we need actually N+2 at least. So our lemonade price is going a little bit up on this one because they're depreciating over a long time. Now, the season begins, and it's getting cold. The winter is coming. Now, hell, our machine is frozen. So we need something to put our machine in to keep it warm in the winter because the water is just frozen. And in the summer, it needs to keep it cool. That's okay, you buy a shed, but then a blizzard comes in and knocks out the electricity. We can work with generators. We can, up to 4 hours, can do with generators, but solar panels are also an option. Our price is actually going up again. It's actually quite bad. So, but the winter is over. And now all the snow is coming as a flood down. And our public water is no longer suitable for consumption. So we need a purification system. That's okay, our price went up a little bit. But then the summer comes, and what happens is that everything is so dry, there's this drought and we don't have any water. So we might want to buy mineral water, or we can build a well, which is cheaper. So let's build a well. But it doesn't help because it was so dry that now we have a lot of fires actually killing our lemon trees. And meanwhile, our service is no longer profitable, not even close. Now, for how much do we actually want to invest to sell lemonades for $250? This requirement actually made no sense at all from beginning on. We don't need 100% availability on a service that nobody uses at night. So, my endpoint is, what you actually need is what customers are willing to pay for. And anything that we can do to raise our availability without making our costs explode. Thank you very much. My name is Igor. See you later.
Right, okay. So who else here knew that Ian McKellen was in a sitcom called Vicious? Right. Yeah, so this let me set up a kind of a tenuous Ian McKellen theme throughout my slides. It'll pay off towards the end of the deck. So I'm Laura Nolan, and this talk is about understanding feedback loops in our systems. So imagine we have, the world's simplest distributed file system like this, and it breaks up data into blocks, which are replicated, let's say 3 times, because 3 is a nice round number for this. And what we're going to do is we're going to loop through, and we're going to check for each block, is it on a machine that's heartbeated okay recently? Does it have enough replicas? And if it doesn't, we're going to kick off a new replication process for it. Simple enough. So it's going to look a little bit like this. We have 4 servers up at the top. We lose one of them, and we kind of get this cross-copying replication of our blocks. Cool. So what next? Right, this is all very well until one day, because computers are terrible and they're in racks which have highly correlated power and network and all sorts of things. One day we lose a rack, and what happens next? We're going to get a lot of replication all at the one time. And you still wanted to connect to those machines that you're heartbeating? Oh, I don't know about that. Their networks are very busy at the moment. So I've seen this in reality, and I expect many of you have as well. So this is the system that we're going to kind of use as our motivating example to look at this really useful thing called the causal loop diagram. So it's a vicious cycle. And here is Ian McKellen in 1969 on a motorbike. Yeah. Okay. So causal loop diagram, it's a cognitive tool for you to understand feedback in your system better and sort of understand some of the dynamics of how things happen in your system. It's a tool for understanding complex systems. And it was invented by this person here. This is Jay Forrester. He was at the MIT Sloan School of Management, and he invented this whole field of system dynamics. He's kind of one of those giants in the systems fields. And he was a very big person in sort of early computer modeling as well. So this is not quite a causal loop diagram yet, but we have the concept of replication, like we saw in the code. Increasing replication, we see an increase in system load as we're copying blocks around. And if the system load passes a threshold, we're going to see failed heartbeats. So we put these plus signs by our boxes, and that indicates that an increase in the one thing leads to an increase in the next thing. So these are not the only things that are happening in our environment. We've also got write load and read load. And we've got things like hardware and power failure, which can also contribute to failed heartbeats. So your system diagram, it's not just necessarily the one part of your system that you're focusing on right now. It lets you sort of see how the environment influences your system. So now we have this new concept, this replicas per block. As we replicate, we increase the replicas per block. And after some time, when the replication is finished, so we have this concept of delay, the system load finishes, or it reduces. We see that this loop in the middle, this is a feedback loop. It's a reinforcing loop. That's why it's got this or in the middle. And that's because one thing increases the next thing, increases the next thing. So if it lets us sort of look at what's happening in our system. So one of the things that we often do to fix this kind of problem, to make it less dangerous, is we add more delay. So here in green, we've added a delay to balance the failed heartbeats. So we're not going to replicate immediately. We can also add a sort of a balancing loop to control our outer loop. And that's a rate limiter, like a token bucket rate limiter, where we increase tokens over time and decrease them as we do the work. So we can use this to sort of visualize how we can make our systems better. What else can we do with it? Well, if you're a wizard, you can do quite a lot. So this is something that some very learned people did with this system. This slide is going on a long time. This is a book called Limits to Growth from the 1970s, where crazy people, tried to model kind of all of human population and civilization and agriculture and figure out when we were going to sort of hit our Malthusian hard stops. They've modeled like water and soil erosion and everything. If you are Gandalf and Magneto, you might like to try this, this is a giant causal loop diagram of both the politics and the geology of an aquifer system in the US. It's quite an amazing thing. So thank you very much, and goodbye.
Hello, my name is Amir, this is Doron. We're from eBay, and we'd like to talk to you about Flamegraph as a meeting point between developers and SRE. I'm a developer. And as a developer, I know my code, I also test my code. By the time my code reaches production, I know it is absolutely perfect.
Well, I work as an SRE in eBay, and we are responsible for the reliability, availability, and performance of production services. And unfortunately, Amir, I see that your service actually has a performance issue in production.
But look at the results of my performance test. I tested it in a performance test environment, and I know it is perfect. Have you checked the network latency?
Well, I measure many things. We measure many things. And my metrics suggest that it is actually not a network latency, but rather your service is saturated and cannot cope with production load for whatever reason. At eBay, we have various production metrics that developers can't really faithfully reproduce in their development environments. And they usually come to us to analyze and triage performance issues in production. And to solve performance issues in production, you have to have a common view between developers and SRE that is both global and also enables us to drill down into a single line of code to triage the performance issue.
Flamegraphs, developed by Brennen Greg out of Netflix, are a visualization of profile software. They show us the results of sampling profiling, whether it will be CPU, memory allocation, whatever has a code path. And in a single image, you can see the entire process sampling, but you can also drill down to a single frame, and you can see the self-time, the total time, how did we arrive at this particular frame, and where do we go from this frame? It also has color schemes, which allows us to differentiate between different types of frame. So we can differentiate between user mode and kernel mode. In this example, Java and JVM as well.
So let's look at some, sorry.
Yeah, our experience shows that using Flamegraphs is a good common ground that allows us, both SREs and developers, to cooperate, to reason about, and to solve production issues.
Let's look at some real-life examples. Well, in this first example, it's very easy to spot that we have a garbage collection issue as a significant time of CPU is spent on running GC cycles within the application. And after a bit of tuning to the JVM, we can see that the ratio of GC to actual code running in the application is reduced significantly.
Flamegraphs can also be searched. In this example, the search results are shown in purple, and we could prove to the development team that far too much CPU was spent on querying embedded Solr index. And actually, that was at the heart of the performance issue that they witnessed. In this example, almost all the CPU was spent doing parking of the thread. And that came from an open source library of queues, and that meant that the queue was simply full, and the CPU was just waiting for the queue to drain. That's a queue size misconfiguration. Flamegraphs are also very good at just giving you an example of an image of a process that you don't even know about. This is a picture of recursion.
In this example, we can actually see the JIT compiler CPU cycles within our application as it starts up. And this is another advantage of profiling our application in this manner, in which you can see code that is not necessarily your application's code. In order to enable this in eBay, we basically created an automation around profiling, and any SRE or developer can generate an on-demand flame graph for any production host very quickly and efficiently, and all snapshots are stored and aggregated and can be searched and browsed by anyone as a starting point to discuss and analyze performance issues in production.
Thank you. Come and grab us for any questions or comments.
Hello and good morning. Hello and good evening. I'm Susobhit and I'm from VMware India. Today I'll be speaking about my slide that is smart and effective way to reduce distributed tracing overhead. So, as from the morning talks, we concluded that there are many tracing mechanisms that we use, but as we all know, there's a major drawback in them that most of them try to randomly sample the data that the traces come in. So how do we reduce this basically? Do we not have solutions now? Are there no smart solutions available today? There are many vendors which provide that. But the main issue with them is they use basically random sampling, which is which basically doesn't capture all the traces effectively. It mostly is skewed towards those traces, which generally gives like maybe 200 OKs. The 401s, the 4XX, the 5XS are really omitted out when these traces are captured. Then, why is tracing so important in the SRE world? That's because with the advent of distributed systems and microservice architecture, we have millions of calls going into our system each day. We need a proper source of truth so that we can root cause any problem going forward. Like if tomorrow some problem occurs, how do we know that till where the trace calls went? And after that, how do we triage it? How do we find the root cause of it? Or if not, tweak our alert mechanisms. The present solutions that are present generally try sample somewhere between 2 to 10% of the whole traces that come in. That's in general. There are systems which do 100% sampling, but yeah, then there's overhead of storage, compute, etc., etc. So how do we, so what we try to do is we basically focused on this particular sampling rate problem of the tracing systems and try to basically have a solution around it. So yeah, just the drawbacks which were already existing was we found out is when we use the existing solution is we found like around 98% of the traces were the traces that we all know that did not point out to the root cause of the problem. Those were mostly like if the traces that were already in use and all those. And as a SRE, we all know that every failure is actually a success in the making. So what do we do? How did we solve this? We actually had a good, quite smart solution to it. That is, we used a smart adaptive sampling way using some bit of statistics to it. What we did is we basically used density-based scanning in order to basically cluster all the traces based on features such as the response time, the response code, the path that it took, the HTTP codes, everything. Those were clustered at the traces under this particular features were clustered into one cluster, and the new traces which were coming up were then classified based on these. So how does density scan work is, you have a particular density set for a cluster. So if there are less number of data points in that cluster, that cluster's sampling rate goes up. If sampling rate goes up, it means that the new batch of traces that are coming in, those needs to be sampled more into that particular cluster, which have a more higher clustering rate. That's what the smartness of the solution was. So how effective was it? We were about to reduce our storage, the persisting of the traces by about a third of it. And we saved a lot on the storage. Secondly, we were able to give more weight to the traces, which actually had a certain root cause element to it, so that going forward we can use them to root cause and triage our solutions. And the most important thing was it was made to be more generic. And yeah, we actually felt proud of it because we could actually see the impact in the main systems going forward. Thank you.
Hello, I hope everything's going well so far. 20 seconds, quite long. So if you follow the news, you probably have seen headlines like those. Some issue on the BMC affecting some security, some USB device can compromise your system, or some other from our friend at Cloudflare, where they discover some random crash on the machine affecting their system. What are those problems have in common? They are both coming from a bad firmware. And the solution? Doing a firmware upgrade on your machine. Sounds simple, can be a bit more complex than that. I'm Yannick Brosseau. I'm a hardware system engineer at Facebook working on firmware automation management, and I'm here to tell you the truth about your hardware. It's in fact just a pile of software all together with a little bit of silicon. So, we are at SREcon. We are getting pretty good, I imagine, at deploying our application. We do it fast, we do it frequently, we do it in a safe way. We might even do that for our system, the platform, the operating system, the supporting tools. But as you talk about the bottom layer, all the firmware lying around in your data center, in all your different hardware, and having thought of managing that and making sure it's running the right version, and you're not finding bugs that we've seen earlier. I'm talking about hardware. Obviously, if you're on the cloud, you don't have any, doesn't care about it. But if you own machine, or especially if you provide machine to other as part of a cloud provider, thinking about firmware is a subject that I want to convince you that is important. What are they? Some obvious one, BMC, BIOS, some more obvious one, microcode, or even like the voltage regulator on your motherboard that provide power, as some software running in them. Some of the more obvious one that we probably managed before, network card. It's everywhere. It's obviously running software. Networking is quite a complex problem. I want to highlight that some of these firmware have a full operating system running in them. Some even have a full Linux stack. So they can be quite complex. Storage element, yes, also software. Hard disk, SSD, all doing different role to make sure all your hardware, all your device give you optimal performance and hopefully give you back the data when you ask for it. And there's many others. Network switches, backup device, power supply, UPS. I'm not even talking about all the building subsystem like AC or other things. These things creeps out everywhere in your data center, and once in a while people come to you like, oh, I need to update this thing. But why we, as SRE, should we care about that? There's many reasons. First, as I mentioned in the beginning, security. These software bits, especially if some of these components are on the network, can affect the problem. You don't want to have intruders just accessing the data. And some of the devices, like the BMC, can even access different parts of your memory. So it's pretty important to make sure all these devices are properly secure in your system. Stability and performance. Like a software in your hard disk gives you more throughput, or various things can create random crashes on the system. So you need to manage those software in the fleet as you would manage any other component of your software stack to get the maximum performance. And you also want to get maybe some shiny new feature. Maybe you get a new BIOS that will give you better power management and will reduce the electrical costs of your data center and save you some money. Or some other thing like new shiny offload for your network device. How do we do everything? I don't have time to go in all the detail. We build a platform to manage the firmware, but I'll give you the few highlights that I think should be important. So the first one, we decided to package every firmware in the same way. They are coming from a lot of different vendors, and we decided to just put them in the same format so all our tool and automation can proceed the same way for every device in the fleet. The second step, we need to know which version is running in the fleet. So you need to be able to track and store in a database what are each of the versions of the fleet. That means you need to be able to query the firmware version that we have. And you need to know which one it needs to be run. Testing. Each of the vendors that provide you hardware and firmware, they do an extensive set of testing. Should you trust them? Probably, but you might have some really corner cases that when you want to continue validation. And finally, deployment. You need to be able to push the firmware in the fleet, and doing that, in most cases, you need to reboot the machine, so that means you need to take down every machine in the fleet. That sound easy, but it actually can be harder than it actually is. A bit of light, as a last note, there's a bunch of open source firmware coming up that hopefully will help us to do management, also squash bug, and be able to contribute more to that area. Thank you.
Hello, my name is James Renken. I use he, him pronouns, and I am an SRE at Let's Encrypt. I'm here to talk to you today about a few additional controls that you and your organization can impose on getting TLS certificates issued. So if you're not familiar with Let's Encrypt, we're a free, open, and automated certificate authority. We have an open API that lets you request a certificate using the ACME protocol. And other CAs and other certificate management products are using ACME as well now. There are a pretty wide variety of reasons you might want tighter controls on issuance, and some good reasons are auditing, or if you want to enforce good practices throughout your organization for key management. And what's at stake is really the purpose of TLS itself. If an attacker can get a certificate that you didn't authorize, and they're in a privileged network position, they can impersonate your service. That's obviously very bad. Now, domain-validated certificates, or DV certs, are one of the types of certificate. They're the only one we offer, and many other CAs offer them too. They only attest that the requester was in control of the host name. They don't attest identity. So we and similar CAs provide a random value you can put in a DNS record or in a file on your web server. We check that it's there, and then we issue. So the first type of additional control that you can impose on issuance is with a CAA record in DNS. In this example, only Let's Encrypt can issue a cert for gchq.dev. Now, currently, you need to have a relationship with a CA where they will agree to restrict issuance for your domain. Otherwise, even if you use a CAA record, anyone else can go to that CA that you've chosen and request a cert and get it issued, if it validates. But very soon, ACME will let you request these controls from automated CAs like Let's Encrypt. So in this example, only this ACME account ID can issue for gchq.dev. You can also restrict the validation method. So you can, let's say you don't want your web front-end team issuing certs, only your DNS infrastructure team. You can do that with these new, soon-to-be finalized extensions to CAA. I'm really, really excited about this extension to the CAA standard because it will let every organization get more elegant, more controlled, and more automated certificate and key management. That's really, really exciting. But it's not all good news. CAA records still rely on the integrity of DNS, which is sometimes marginal. An attacker, if they put themselves in between a CA that's trying to validate control and the DNS servers of their target, possibly with a BGP hijacking attack or something similar, then they can get a certificate that they should not have. BGP hijacking is getting harder, but it's not a solved problem. So what can you do about this? Having good global presence for your DNS servers is very important because the attacker doesn't have to trick your CA or a particular CA. If they can trick any CA anywhere in the world, then they could potentially get a malicious cert. Another option, in addition to good network operations, is to use DNSSEC so that your DNS records can be authenticated. But this is not always great. There's a very, very serious operational trade-off for the security that you get from DNSSEC. It's very difficult to operate, but it is the only way to get authenticated DNS right now. So what we recommend is that you both prevent malicious cert issuance by publishing CAA records and using good practices, but you also monitor the internet for unwanted TLS certificates. And you can do that because Chrome only trusts certificates that have been publicly logged. So there's a very strong incentive for CAs to do that. And these certificate transparency logs are public, and there are a number of services you can use to monitor them. You can also build this monitoring into your own clients so that they won't accept certs that have not been publicly logged ever. So your monitoring is then more effective. I have a few resources here in the slide deck. Certificate-transparency.org is sort of the authoritative resource. And that's what I have. Thank you so much.
Hey everyone, my name is Brennen Smith, and while we let this change, I am the head of the systems and infrastructure engineering teams for Ookla, so the company behind speedtest.net, Down Detector, and a few others you might know. So, all right, we'll just get going. I'd love to take the opportunity today to tell you about the core of our service routing and discovery engine, a stateless service mesh that we've lovingly named Copilot. When designing a user experience, it's incredibly important to think about the 100 millisecond bound. When a user performs an action and it responds back in 100 milliseconds, the human brain will perceive this as roughly instantaneous. Conversely, if it takes longer than 100 milliseconds, the user will perceive lag. This lag has a tangible, outcome. Amazon found that for every 100 milliseconds of additional latency, this cost them 1% of revenue. So overall, let's dive into, let's keep 100 milliseconds in mind, and let's dive into the motivational reasons why we built Copilot, our own service mesh, and also how it enables us to hit this number. So, I'm a little ahead. In a few seconds, you'll see a diagram of an essentially Amazon load balancing system, a generic one. And what we can see here is there's multiple, so ultimately, you can see that there's multiple availability zones. Each availability zone is one or more data center that's geographically distributed across a macro region. Now, the logical networking plane within a region is essentially flat. However, we can't beat physics yet. There is a cost going between availability zones. In addition, there's also a monetary cost. Amazon charges $0.01 a gig to go across this boundary. Now, the way that these load balancers work is they provide a DNS address, which is an A or quad A, that has all of the IPs for all the load balancer nodes and all the AZs. So assuming a nice even round-robin distribution, there's a 66% chance you'll jump AZs to get to the load balancer. On the load balancer itself, you have a nice spread across all the backend instances, so there's another 66% chance you will jump AZs. What this means is there's an 89% chance that your request will at least cross one AZ boundary during its lifetime. And this is ultimately what Copilot aims to solve. So Edgar Dijkstra famously said, simplicity is the prerequisite for reliability. And this is the cornerstone of what Copilot is built on. Copilot was built with two principles in mind. One, very simple, keep all the traffic local to the single AZ unless there's an anomaly. And the second principle is that we want this control plane to be as simple and reliable as possible. So let's talk about the first principle. It's very simple. When things are running normal, Copilot isolates traffic to the local availability zone. However, when there's an anomalous event, this is where it gets fun, is anomalous event ranging from just an ASG resource imbalance all the way to a catastrophic service failure, Copilot will instantly ratchet open and spread traffic across all availability zones. This provides us in normal operating conditions, vast majority of the time, we have the performance and cost benefits of running single AZ architecture. However, we still maintain the resiliency of a multi-AZ architecture. And the second principle ultimately comes down to how we built it. So we actually built a serverless engine that leverages multiple regions of AWS S3 as a control plane. So we don't have to, unlike other service meshes, when we have to rapidly scale the mesh, say in response to a DDoS, we can do it very quickly and without having to worry about the control plane. This is essentially a set of timings over the course of 2 months when we were looking at rolling out Copilot. Now we can see on the Amazon load balancer that there's massive amounts of jitter and latency and deviations. And actually on September 19th was a breaking point. There was massive increase in latency and we had to do something about it. And that was when we built Copilot. On October 2nd, we rolled it out globally, and we can see the massive reduction in latency and jitter in timings across the board. Now, for the eagle eyes out there, you might see on the y-axis, this is only a factor of like 8 millis. We're not talking massive numbers here. But let's think back to the original part of the presentation. We live in a microservice world. And for a given macro request, there's many, many sub-requests involved with it. And say, for example, we have a request, it has 4 sub-requests under it. and each one has an 8 millisecond tax attached to it. That's 32% of your 100 millisecond budget burned simply on inefficient routing. So overall, we're super excited to showcase Copilot to the rest of the tech community. It's really easy to implement, really easy to bolt into an existing infrastructure. And given more time, love to talk about more on how it works under the hood. Feel free to find me later in the conference or reach out to me directly. My name is Brennen Smith. Have a great day.
Thanks. Can we keep it going for whoever made these sweet graphics? Yeah. Is that you?
Effie.
Oh, you're welcome. Okay. Sorry? Oh, no, I'm okay. So I'm Jane, and I am an engineering recruitment manager for Shopify. I came in from Canada, and I must say I felt immediately comfortable when I arrived at the exhibitor hall yesterday because the temperature in here was the exact same as it is back home. And personally, I'm not a huge fan of slides and don't typically use them for my presentations. However, I was asked to put together a deck, so I obliged. I must warn you though, these slides have absolutely nothing to do with my lightning talk. I thought I would just share a bunch of interesting photos of our office and even more interesting photos of my dog. His name's Bauer, so stay tuned for that. So try to just pay attention to what I'm saying, because again, the slides in no way reflect what I'm about to talk about. So let's get to it. Choosing to return back to work after an extended period of time can be really daunting, especially in an industry as fast-paced as tech. That feeling can be intensified. So we want to make this choice easier to improve our industry for everybody working in it. Why did we do this? We have a constant need to hire senior engineers, and we're facing challenges, like I'm sure all of you are as well, judging by all of the yellow tickets I saw on the name tag saying we're hiring. So we're having trouble identifying people to fill these roles. Many great engineers, especially women, choose to focus primarily on parenting for a period of time and then face multiple challenges when trying to re-enter the workforce. Senior engineers are also much more likely to be parents just due to time served in general. So showing people that we're parent-friendly is a big win. It's much easier and it's much faster to recover skills rather than learn them from scratch. And then rusty engineers also have a work history which is predictive of future success at Shopify. It's probably more predictive than evaluating potential in inexperienced employees. It's also just the right thing to do. So it's a great opportunity to provide to people because we have the means to do so, fortunately. Where are we at here? All right. So these are the success metrics we identified. Convert at least 8 participants from the applicant pool. We ended up getting 30, so that was a welcome surprise. We'll retain 75% of participants to convert to full-time. We will fill 4 senior engineering roles that are on the docket right now. And last and probably the most important one is that we want community support. So therefore, we're aiming for about 75% of participants to feel better prepared to re-enter the tech industry after finishing this program. So we'll survey them at the end. So how did we do this? Well, it started with me basically cornering people in our hallways and the lunch line or sliding into their DMs to see if they could help me. Pulling this thing off was going to take a lot of different stakeholders. So we needed mentors. Each participant in the program is guaranteed a mentor for the duration of the program. This also affords new leadership opportunities to our existing senior devs that might want to jump into people management. We needed R&D, learning and development, so the people who would build our curriculum. Internal solutions, so who's going to book the rooms, order the swag, that kind of thing. And then IT, so who's going to be providing laptops, granting access to our systems, things like that. And then once we got everyone on board, I wrote the job descriptions, and the criteria was that they needed to be out of the software development industry for a minimum of 2 years. Prior to that, they needed to have 3 years of experience as a professional software dev. And the last thing was a strong foundational knowledge of object-oriented principles and fluency in at least one object-oriented language. Even if they were super rusty, it was fine. Okay, kind of power through this. So we also decided to make the class hours from 9:30 to 2 so people could send their kids off to school and be around to pick them up. And also another important thing to note is that we're paying these people. So this is a fully paid like education program. Once the job descriptions were posted, we started to engage media for promotion. So we used a combo of targeted Facebook ads, print media, radio, and local news channels, and ended up gathering about 150 applications. We kept the interview process super simple. There was no point in doing technical interviews at this time due to the candidates' backgrounds, so we just did calls with them, asking them to walk us through a project from start to finish, because if we could get a sense of what they were able to do in the past, that would be a strong indication of what they will be able to do in the future. Okay. Oh, wait. So one quote that I got from a candidate was that this program was actually a gift from God. I think I wouldn't necessarily go that far, but it was nice to hear nonetheless. Thank you.
It's not easy being last. Whew. It's a lot of hard acts to follow as well. Yeah. So, managing on-call atrophy. So what's atrophy? Atrophy is when you don't use a muscle. And because you're not using this muscle, you eventually waste and you just can't do it anymore. So what's on-call atrophy? So on-call atrophy is where you're not using your on-call muscles. And what are these muscles? They're the software that you use, your ability to access the platform, authentication, firewalls, firewall ACLs. And how does this happen? Well, low call rates. Maybe your system is super reliable and you never get a call. Google calls this operational underload. And it's a problem, and I'll explain a bit more why this is a problem. Another reason is if you've got a massive product base. You have that legacy system that nobody knows about, nobody gets a call on, and when you do, everyone goes, oh, what the hell was that? Another problem is you have a really infrequent load rotation. And this is a big problem if you are not in touch with the platform all the time. You go on call, 6 months later, you're on call again, and everything has changed. The world has changed around you, and you don't know. So I'm saying not being paid is a bad thing. I know we all want the universe of never getting woken up at 3 in the morning, but sometimes this can be a problem. I'm going to start trying to explain why. No system is 100% reliable. Never, ever, ever will it be. So that means you have to prepare for when you are going to have a problem. Because in a long enough period of time, the fact that you're going to hit problem hits one. And if that period is too long, people don't know what to do. So this is where you need to start really practicing your muscles on a regular basis. There's another problem as well that you can hit. It's around emotional safety. We have an engineer who said after a year being on call, because he hadn't got a single call, he felt more stressed than his first week on call. And that was because he no longer felt he was able to actually take a call. He hadn't got called. Last thing is to be prepared for now. So what's that mean? Your first time is on call, you've set up all your hardware, you've checked everything, your firewall, your ACLs, everything's cool. Then you don't get a call in 6 months. And in those 6 months, APIs have changed, people have put a different ACL, the VPN, the software has changed, you can't connect, your software is out of date. Okay, this is a problem. So you need to make sure you're always prepared to the current state of your platform. So we did this really stupid thing, and we started paging people at random, okay? Now, we're not monsters, okay? And don't freak out. There was some strict, wow. Oh. Yeah, we some strict real reasons out this. First of all, it was opt-in. All the engineers agreed to it. The call would only happen between 6 and 9. You would only get called once. And if you got called a real call, you didn't get called the firewall call. We set up a set of comprehensive drills that covered every platform. Each drill was a simple routine to follow, tested connectivity, tested CLI or tools and so on. So a typical one might be connect to such and such a platform, tell me how many pods are running on such and such a cluster. and then you log down to PagerDuty, close it off. That's cool. It also covers across all of our product base. All the stuff that we're on call for, that's what we have. And so we found out a few things. We found out people weren't repaving their laptops. We found out that Google does really weird things with IPv6 on their firewalls. We also found out that the engineers liked it. And that was really weird, okay? So, obligatory war story. So many, many moons ago, we had this platform. We were supporting it. It was super, super reliable, okay? We never got called. We actually had engineers who didn't know we supported the thing. And I had a call, and the RSA keys for the VPN had all died. So I had to jump in a taxi, cross town, get to the data center, argue with security, get the local engineer on site. It took us an hour to find the physical server and hook it up to a KVM, and then 5 minutes to fix. So, my name is James Wynne. I'm an engineer manager in Pivotal Cloud Ops, just up the road there if anyone's wondering. Drop me a mail if you want, and come up and talk to me afterwards if you have any questions or comments, or you think I'm crazy. Okay.
Cheers.